Okay, our next topic in thermal physics is the first law. And the first law relates to internal energy. Now, this is also known as thermal energy. And what that energy is, it's the energy of molecular motion. And it's the total kinetic and potential energy of that motion. Now, the symbol that we're going to use for internal energy is a U. Now, there's a couple of ways that we can change the internal energy, and the sort of materials we're talking about here might be, say, like a circulating refrigerant in a heat pump. We might be talking about steam going through a cycle in a boiler. And these fluids, the circulating refrigerant or the steam, all undergo changes in internal energy as either we do work on the fluid or heat is transferred in or out of the object. In or out of the fluid, sorry. So, work is W and heat is Q. Now, the first law of thermodynamics just states very simply that both of those are equally effective in changing the internal energy of a fluid. So the change in internal energy of the fluid is related to the amount of work done on the fluid plus the heat flow in. So the internal energy goes up if work goes in or if heat goes in. It'll go down if heat goes out or work goes out. Now, we're going to, in our definition of work, say that we're looking at the work done on the fluid. This is going to be work in, right? That work, if you do work on the fluid, that increases the internal energy of the fluid. It's also possible that the fluid itself does work. And when the fluid itself does work, the internal energy will go down. So we could sort of look at the bar chart here. This is sort of representing the first law of thermodynamics. So the change in internal energy, I'm going to say this is U initial and this is U final. So delta U would just be final minus initial. And so what we're seeing is here, we started off with some internal energy. We did some work on the fluid, so that increased the internal energy. And there was some heat flow into the fluid. And as a result of that, the total final internal energy of this fluid is equal to the initial energy plus the work that was done plus the heat that flowed in. Now, you can see we're already introducing some sign conventions here. When we write the first law of thermodynamics in this form, we're saying that work done on the fluid is positive and work done by the fluid is negative. Similarly, we say heat flow in is positive and heat flow out is negative. Those sorts of distinctions and those sorts of sign conventions are summarized in this chart. And there's some subtle things that you need to understand here. And these things will be illustrated when we start talking about thermodynamic processes, which we're going to do right now. The first thermodynamic process is a constant volume process. Now that can be called isochoric, or probably a better term is isometric, because metric just refers to size. So isometric means constant size, i.e. constant volume. So if we have a constant volume process, so say in our refrigerant cycle, it's possible that we change the pressure, but we allow the volume to remain constant. So how could we do that? Well, we could fix the volume of the container and then allow thermal energy to flow in or out of it. That will be a constant volume process. Now, with the volume being fixed, that means there's no displacement of the gas and therefore no work is done. Now, the first law of thermodynamics says the internal energy changes if work is done or if heat flows. And the internal energy goes up if you do work on the gas and if heat flows in. If there's no work that's done, then the change in internal energy only happens or only, or sorry, only depends on the amount of heat flow is what we're trying to say. Now, heat flow, we know from elementary physics, is given by mc delta T, where m is the mass of the object, c is the specific heat capacity of the, I should say m is the mass of the fluid or material, c is the specific heat capacity of the material, and delta T is how much the temperature goes up. Now, we've used this relationship before, but for solids, there's only one value of the specific heat capacity. When we are doing thermodynamic cycles, often we'll be dealing with gases, say like steam. And it turns out that there's actually different specific heats for gases depending on the process. If there's a constant volume process, then we reflect that by saying it's a constant volume specific heat by putting this little v down here. So CV is the specific heat capacity at constant volume. It still has the same units as before. It's joules per kilogram degree centigrade or joules per kilogram Kelvin. But this value, or the value that we use, reflects the fact that this is a constant volume process. We're going to see later that for a constant pressure process, the number is different. Now, this is the mass version. There's another way to write this. You can make C the molar specific heat capacity, and then this relationship would be N, and then there's a small c instead of a capital C, CV delta T. And so this is number of moles, this is joules per mole Kelvin, and that is the temperature change. And you can see that these two specific heat capacities are just going to be related by the units of kilograms per mole, i.e. the molar mass of the refrigerant or of the fluid or of the material. Now, it's customary to represent thermodynamic processes in a PV plane, especially if we're looking at a gas as being the thermodynamic fluid. Now, there are many pressure units. You could use atmospheres, kilopascals, psi's, whatever, and volume could be cubic meters or liters, whatever you like. So we won't label those with units. The units will vary with the problem. But what we will do is we will say, when we're looking at this isometric process, this constant volume process, a line of constant volume is going to look like this in the PV plane. So that is an isometric process. Okay. So to summarize then, what we've seen is that for an isometric process, constant volume, the change in internal energy, the delta U, which we know by the first law of thermodynamics, is work done plus heat flow. That's just going to be equal to the heat flow. The work done is 0, and the heat flow is mCV delta T, or is N times the constant times the molar specific heat capacity times delta T. Now, let's just do a quick example here. Oh, first let's be reminded of the ideal gas law, which says PV is nRT. P is the pressure of the gas, V is the volume of the gas, N is the number of moles, R is the gas constant, T is the absolute temperature of the gas. Now, it depending on what units you're using, you will select from various versions of the gas constant. So if you're doing your pressure units in kilopascals and your volume units in liters, then you would use this version. If instead of using kilopascals, you're using atmospheres, then you would use this version here. Now we're going to use this a little bit of apparatus, and we're going to demonstrate a constant volume process, and we will produce a nice PV graph for it and see that it agrees with what we had on the previous page. So we'll fill that in class. But let's do a numerical example here now, and of an isometric process. So we start off with 2.5 moles of an ideal gas, and here we've got the molar specific heat capacity, and then we, at constant volume, the pressure increases. So let us now, well, first we can visualize that in the PV plane. So let's just sketch that graph. So here's the pressure axis. Here is the volume axis. Okay. And let us here so this is pressure, this is volume, and the pressure is increasing from 0.75 atmospheres. So we'll just scale this axis at atmospheres up to 2.5 atmospheres. And this is happening at a constant volume. So it's just going to be going straight up like this. Okay, so we're asked for the volume and the temperature because we're told that this gas here, this was at 275 Kelvin. Okay, so we know the pressure and the temperature, and we know the number of moles. This is N, the number of moles. We should be able to find the volume using the ideal gas law. So PV is nRT, so V is nRT over P. Okay, so we substitute in the number of moles, 2.5. I use the liter atmosphere per mole Kelvin version of the gas constant here because I had the pressure in atmospheres. And the temperature in Kelvin at the initial point is 275 Kelvin. So solving that for volume, we get 75.2 liters. 75.22 liters. And of course that will be the final volume as well because it's isometric and the volume's not changing. In terms of the final temperature, well, we rearrange the ideal gas law and get T as PV over NR. Then we can put in the final pressure of 2.5 atmospheres, our volume here of 75.2 liters. We'll divide by the number of moles, which is 2.5, and then we'll use this version once again, the liter atmosphere per mole Kelvin, and this of course was 2.5 moles, and so what results there is a temperature in Kelvin. It's 916.6666 Kelvin. So the gas is increasing from 275 up to 916 Kelvin as a result of this isometric change. Now, the work done is the thing we're asked for, and that's 0 because there's no change in volume, there's no displacement. According to we can use the next to find the heat flow. We'll use M, constant volume, specific heat, or in this case we'll use the number of moles, and we're given the molar heat capacity. So we'll use this relationship here. So we have 2.5 moles. We're told that for this gas there is 12.5 joules required to change the temperature of a mole by a degree Kelvin. It's 12.5 joules per mole Kelvin. And then how much of a temperature change do we have? Well, we're going up to 916.6 repeating, and we're starting at 275. So this works out to 20,052 joules of thermal energy transfer. Now, clearly, because the temperature is increasing, this heat flow must be into the gas. So there's a hotter object next to this container, and thermal energy is flowing from that hotter object into the gas. Our internal energy must also be going up. By how much? Well, the first law of thermodynamics says that internal energy changes when you do work on a gas or when heat flows in. There's no work done, but 20,000 joules flowed into the gas. So the total change in total energy is an increase of 20,000 joules. So that's an isometric change. The next thing we're going to get you to do prior to coming to class is to think about, what happened there? Okay, is to think about, there's a few thinking questions here related to the ideal gas law. So for each of these next few, so there's that one, and there's this one, and there's these two. Think about them and come up with an answer. And we'll start class by quickly going through those, and we'll then discuss another thermodynamic process. So the first one we did here is an isometric, constant volume. The next one we'll do in class is isobaric, or constant pressure.